Hello everybody and welcome to this final projects presentation ceremony of the Masterclass Batch 2022. Today we are going to have three students doing their presentations, three students who are about to graduate. I would like to introduce very quickly the three presentations so that everybody knows what to expect from this stream. By the way, my name is Alberto. I am the director of the master, and here I have
Ricardo from one of the teachers of the master.
Yeah. So we are going to start right now in just a minute with the first presentation, which is in charge of Stephen Murray. Let me show it very quickly here, and it's titled "First Step Towards ROS to Control on the Solo12 Quadruped."
It's very interesting. The presentation is about how to add ROS2 controllers to a new quadruped that has been is an open development.
Yeah, and we are going to even be testing with a real robot.
Yes,
right?
we have it here thanks to Robotics.
Yeah. Then the next presentation is going to be by Olumide Godson. Yeah, then let's not lose any more time and let's go with the first presentation by Stephen Murray. So, hello, Stephen.
Here. Okay, just a second. We are trying to solve it. Okay, so you cannot see us, people over there on YouTube. Let's see. So,
Stephen, can you try one thing?
see. I cannot hear anybody, not even myself, on the YouTube. Okay. Yeah. This means that this volume is not. So what about now? Yes. Okay, let's see. No. So this is terrible. I cannot hear myself from there. So the sound is very, very low. Okay. Is it better? Hello?
Hello, hello, hello.
Hello? Hello? Hello?
Can hear Ricardo barely. Very loud sound.
Okay, now I think it is. So let's try now, Steven. Steven, can you say something?
Much better. Awesome.
Yeah. Yeah, so we cannot hear Steven for some reason. No, we cannot see you. Let's go to your face then, I think maybe, and then we can see from there. Yes. Yes, so there it is. Steven. Yes, exactly, Steven. We can hear you here at the studio, but it looks like in the streaming is not going. And then our system is coming from here. Nothing. Okay, so we need to test this again. Studio and audio.
Please check Zoom, capture Zoom.
What are you doing?
Oh, I'm just making sure that it doesn't log me out.
Okay. So, yeah, tell me. I need you to be explaining to me. What are you doing?
Wait. Are we starting the presentation? Or?
No. It's just to test. So we need you to talk because the problem is on you talking.
Oh, okay. Okay, you just want me to talk? That's it.
Yeah, we got it.
Right.
Okay, we got it.
I got it.
Okay, yeah, it looks like we got it finally. So let's start again with Steven's presentation. Okay. Then, Steven, are you there?
I'm here.
Perfect. Then,
Everyone hear me?
yes, everybody can hear you now. And then let's start with your presentation. So please start from the beginning. I'm very sorry to put you this pressure on your presentation, but I'm sure that you are going to do an excellent presentation. Then go ahead.
Okay. So my presentation is going to be is about first steps towards ROS2 control on the Solo12 Quadruped. And really my little disclaimer here is that my primary goal for this presentation is to articulate my two main accomplishments. So the first accomplishment was ROS2 control working for a single leg on a physical Solo12 robot. And then the second accomplishment was a website which provides a graphical interface as well as inverse kinematics for ROS2 control on the Solo12. And so just a little disclaimer, the construct puts out a lot of educational content that's really focused on teaching, whereas today's presentation, I'm going to try to explain as much as I can as I go, but today's presentation is really focused on just saying what I did as opposed to teaching. And in particular, one of the requirements for this project were that the students use 3 developer tools. And so I'm going to run through those right at the beginning really quick. So the 3 developer tools that I chose to use were Git, Docker, and web development. So the code that runs on the robot as well as the website are on GitHub. We'll just quickly verify that indeed, yes, this is a GitHub. And similarly for the website. Additionally, the web page that I'm going to be running is going to be served by a web server running in Docker, and that Docker image is hosted on Docker Hub. Wait for it a little bit. Okay, so yeah, here's Docker Hub. And finally, I believe that the web page fulfills the web development requirement because a web page is a web page. So here's my agenda. I talked about really my overall I spent a lot of time on this project trying to get the hardware to work, and so I'm going to go over my insights with regards to that. Third is I'm going to demonstrate the website in simulation. The hardware of the robot is a little finicky, so whereas the website is whereas simulation is more reliable, and so we're going to first demo the website in simulation just so you can get a feel for what the website does. And then finally, I'm going to do a demo on the real robot. So we begin with what is the problem? The Solo12 Quadruped is an open source robot designed by researchers at Max Planck Institute, NYU, and CNRS in France. Because this robot is both open source and also capable of a lot of pretty impressive feats, a community of people has emerged, and all these people in this community, they want to build their own and program their own Solo12 robot. So just look at that real quick. This is the forum that all the people who are interested in this robot post on. As you can see, it's not just the researchers, there are other people too. So clearly there's a lot of community interest in this. A community has emerged with people who are interested in this quadruped. And so PAL Robotics, but you know, building one of these robots is actually quite the endeavor. It can be difficult to source the electronic components that make up the quadruped. There are also a bunch of parts that you need to either 3D print or machine. And finally, the assembly of these parts is not trivial. And so PAL Robotics, a robotics manufacturer in Spain, is trying to make these robots more accessible by selling assembled versions and kits. You can see that here. So if you want one, you could fill out this form and potentially get a Solo12 Quadruped. But in addition to providing the hardware, Power Robotics also wants to provide software to people. In particular, they're interested in providing ROS software for this robot. But Power Robotics doesn't really have the bandwidth right now to work on ROS software. So Power Robotics asked the construct for help with adding ROS2 support to the Solo12 robot. And then additionally, the construct is interested in using the Solo12 robot as a platform to teach ROS control. So therefore, I would say that the work I've done in this project is a step towards the problem of making the Solo12 Quadruped more accessible. So when you put ROS on the robot, that means that people can use the whole ecosystem of ROS packages along with the robot. And then additionally, the web page can be used as both a teaching tool as well as a diagnostic tool. So as I said earlier, the primary challenge with this project was trying to get the hardware to work. And rule number one of any project is not to reinvent the wheel. So I was starting this project, I found a ROS2 control hardware interface that already exists for Solo12's cousin, the Bolt biped, which is in that Git repository there. And Bolt is very similar to Solo12. So in theory, we should have been able to just make some minor tweaks to this and it would work fairly quickly. But in reality, what I found is that this was very flaky. Sometimes the ROS2 control would work, and other times it would not. And the conclusion I've come after trying this for a long time is that I think a lot of the problems came from broken motors. So even if you have good motors and you have bad motors, but I think that enabling broken motors seem to make the robot as a whole less reliable. Here's a picture of one of the motors that we know is definitely bad because it's coming out of its spot. And then additionally, the other thing that we found out is that the code that the quadruped comes with is a little confusing with regards to how you enable and disable motors. So here's a screenshot of a configuration file. And the game is to try to guess which motors are enabled by this configuration file. So the motor numbers are 5, 6, and 7. And so you look at this, you might think, oh, it's going to enable 5, 6, and 7. But actually, the correct answer is that this is going to enable the motors 0, 1, 2, and 3. And because what the code really does is it counts up the total number of motors in this array that you've defined, rounds that up to the nearest multiple of 2, and enables that many motors starting from 0. So in this case, you have 3, round that up to the nearest multiple of 2, that's 4, and then 4 motors starting from 0, 0, 1, 2, 3. And this is fine if you're going to use all the motors, and so that will get you to the right answer. But if you want to test specific motors, this bug can be very confusing. So I rewrote the code to only enable the exact motors that are requested in this YAML file. And then for today's demo, I picked three good motors on a leg, and we'll do that. Now we'll demonstrate the website in simulation. As we said, the hardware, we really only have 3 motors that work, whereas the simulation, we can demonstrate the whole quadruped, all 12 motors. And so we'll start with the simulation. Start with simulation so we can show the full power of the ROS2 of the website. So we'll begin by launching Gazebo. So there's Gazebo. Zoom in a little bit. Okay. And then we need to do we're going to start the simulation, and then we're going to see if the controller appears. Okay, and as we can see, there's a forward position controller, which is taking commands. And so now we'll try publishing to the topic to move one joint. Okay, so as you can see, it moved one joint. And then the other thing we can do is we can use the joint state topic to get the angles. Now you'll notice that in our in the previous command we were publishing the first entry, but here when you go look at the joint state, you'll see that actually it's here. It puts the 4 from the bottom, and so this is confusing, and this shows that, you know, trying to send angles via typing in this command line and looking at the angles with the joint state is difficult. And so this is part of the motivation for the website. The website will communicate via a ROS-Bridge WebSocket. So the code of the web page will talk to the website, we'll use a WebSocket to talk to this web bridge, which will then talk to ROS2. So we'll begin by launching that. Okay, looks like that's started. And additionally, we'll need to start we'll start a web server to serve the website. Now we need to get the URL of the web page. So to do that, we use these two commands that are particular to the Construct online platform. Now we have the web page address. And here we have our web page. And then the other thing we need to do is get the ROS-Bridge address, which we use to allow the web page to connect. Now that we have the web page, I will discuss the different options. So the first option is between Solo12 and Solo3. There is no Solo3 robot in real life. There's a Solo12 and there was also a Solo8, which doesn't have the adduction motors. But Solo3 is what we're going to use later today when we only test one leg on the physical robot. On or off determines whether or not it publishes to the topics. So when it's off, that allows you to move the sliders to where you want, and then you can turn them on with on. Then we have two different types of controllers, position and trajectory. We'll talk a little bit more about the trajectory controller later. And then finally, we have two different options for the input type. You can either specify the type as joint angles, like what we were doing before, or we can have Cartesian positions, which solves the inverse kinematics and moves it along in 3D space. So let's begin by turning this on. And we'll move it a little bit. And we can see that you can move the adduction motor. We can also move the flexor extension. This is being really weird. Yeah, and trying to move the one on the end. Let's try a different leg maybe. Yeah, this gazebo simulation is going crazy. Yeah, I don't know what's going on here, but there's a joint angle mode. We can also try the Cartesian mode. This is not working at all. Okay. This should be able to move the joints in a smooth way, but this does not appear to be working. So I guess we'll oh, maybe that's it. Okay, haha. I have this also publishing, so it was fighting itself. That would make sense. Maybe. Okay, now we're in joint. Yeah, there we go. Okay, so you can see this is the Cartesian mode. It's going up and down. And then this one should move it side to side. Side to side doesn't work as well. But then this one is forward and backwards. Okay. That's Cartesian. And then the other thing we can do is we can do trajectories. So we'll stop the gazebo and we'll do the gazebo. The gazebo trajectories. So while we're waiting for that to come up, as part of this project, Luca from PAL Robotics came out to give us some advice. And one of the things he told us was that when you're sending a trajectory or waypoints to a robot, you want to try to keep the frequency that you send out these waypoints even. You want to have even time intervals between each waypoint you send out so that it doesn't isn't too jerky for the robot. And so ROS2 Control has a built-in solution to that. It's called the trajectory controller. So we'll try that now. Turn it off. And let's just try moving. We'll do joint angles this time. Okay. And then when I turn it on, it should do the motion. Okay. And we also need to start the simulation. So as we can see, it publishes trajectories. So instead of the jumping that the position would do, the zooming off to the position, we set the trajectory to move the position very smoothly. So that's the demo for the website. Now I guess we'll try on the real robot.
So Stephen, I'm here with you. Then I'm going to follow your instructions about how to show the real robot on this camera.
Okay. Okay. So first thing I do with regards to the real robot is similar to the simulation. I have to start the Ross bridge.
Hello, Stephen, can you hear me?
Hello. Yeah.
Okay, so here I am with the camera on the robot.
Okay. And then the second thing I need to do is run the do the web page. And the third thing I need to do is start up the ROS2 control hardware interface. It needs to be root. Okay, so it sounds like it moved to the 0 position.
Yes.
So that's a good sign that the robot is working. Let me bring up the web browser.
Stephen, we lost you?
Yeah. You lost me?
No. There you
Yeah,
are.
sorry.
Sorry.
So let's see, here's the web page. Ross web page. No, this is not the right web page. I just need to find the web page. Here's the web page. Okay, I'm going to turn on the position controller. Let's try moving one of the joints. Anything? Yeah, so as you can see, we're moving that joint there. I'm just sending position values, and we can do the same thing for that motor. And finally, we can do it on the adduction abduction.
Yeah, let me change the camera angle for the adoption. Can you move it again?
Yeah.
Yeah, I think it's clear.
Okay, and now we'll try in Cartesian mode. So this might jump, so be ready.
Yes, I'm ready.
Okay. Yep.
Yeah, there it goes.
I guess we'll start out with up and down.
Yes, that's it.
So you notice it's moving up and down in 3D space in a straight line. So it's doing math to figure that out. And then forward and back. You can also do that. And then this one, side to side, doesn't work as well.
There it goes.
Okay. So that's the position. Now we'll try trajectories.
Okay.
So let's try joint angles for trajectories. Okay. Okay. I mean, yeah, there's. Do it again so you can just see one joint.
There you go.
This is smoother than the other one. And I guess so we can do one last one. Okay, yeah. So I guess that's the demo. I guess we'll conclude with lessons learned in future work. So I don't think we need the real
camera. Yeah. Okay. Stopping.
So I guess my lessons learned was I spent too much time running experiments with all the joints. I think having bad motor, some of the motors that aren't as, some of the broken motors, when you have broken motors, it impacts how well the other motors work. And so probably should have started with doing experiments with smaller number of joints earlier. And then I also learned that trying to debug hardware remotely is really hard. You know, a quadruped is this very 3D thing, and it's hard to tell from maybe just one webcam exactly what position it's in. For future work, we could work on, we did a lot of work trying to get calibration to work. We didn't quite get it to work, but maybe now that we've identified 3 motors that we're happier with, we could try calibration again with those motors. The other thing we could do is right now, all we're doing is we're publishing to the position interface. This robot actually, not in addition to position, also has velocity, torque, KP, and KD interfaces. And so more sophisticated controllers would utilize all those interfaces. And finally, a lot of the ROS2 controllers really seem to come from programming arms to move from one position to another, whereas a walking robot really isn't just about moving the leg to different positions. It also needs to exert forces on the ground. And so work could be done on one possible approach to trying to control the forces you exert on the ground would be an impedance controller. But I guess that the point is that writing controllers that actually exert forces on the ground is another area that we could explore. So with that, thank you for listening to my presentation. Hello? Yeah.
Continue with the Q&A section. So you can stop now, Stephen, sharing your screen if you want, or you can leave it like this in case that maybe you're going to have to show us something from there.
Okay.
So yeah, do we have some questions there
Prepared for Stephen?
Yeah.
Yes. So so here one interesting question is if you can explain how you implemented the inverse kinematics, the one that you used for computing, so making the robot move in
Sure.
maintaining the end point, the end effector in the position that you indicate using the sliders?
I mean, I guess the answer is you use math, but do we have a?
Can you show us
I could. I mean, I could show you the equations, but
on the code that is being executed?
okay, you want to see the code? We can see the code.
And the IDE and the second icon?
Yeah. Okay. I mean, basically, the answer is that you draw triangles, but it lives here. Yeah. So we have this function, compute the inverse kinematic, which takes the x, y, and z position of the end effector. Mm-hmm. This LL is the leg length, so the two legs have the same length. And then this offset is the fact that the adduction, abduction, that there's a little bit of an offset from that. So you can solve for the first angle. Is really just a function of how far out you solve for the adduction abduction first, and then once you solve for that, then you know how far away the point is from how far out the point is, and then that gives you the angle between the second and third links, and then finally and then the angle to the point determines sort of the angle of the second link. I really should have drawn a picture. This doesn't make a whole lot of sense without.
No, it makes sense, but it's difficult to visualize from the words. Yeah. And why did you decide to implement this inside the JS file instead of having it inside the, for example, in a node, in a ROS node that receives the data, the request from the web interface, and then it's a special node on the computer that controls the robot that receives this message?
I mean, that probably would have worked too. I guess I thought maybe this was simpler, or this. That would have worked too. Yeah, I mean, I don't know. I think as far as robot go, the inverse kinematics of three joints just isn't that complicated. I guess it doesn't really. Yeah. No, I mean, basically the repository for the biped also had controllers for they had stored controllers for their biped, and so I just used those. You switch out the URDF a little bit. Yeah, they had a simulation for the biped, and then this is a modified version of that to use the quadruped. Yeah. Yes. Yeah. Oh, absolutely. Let's see, what a bunch of different ways. You know, getting the inverse kinematics right. I know we had issues with the demo today, but you know, the first time you write the inverse kinematics, you don't get it right, and so being able to test it in simulation before putting it on the real robot was really useful. That's the main one, and also because the real robot, we were only moving 3 joints, and the simulation we had 12. You know, to before I put it on the real robot, I tested a 3 joint version in simulation first, make sure that it would work. Okay. So I guess ROS2 control, when you think about it, it sort of has 2 parts. One is the hardware interface, and the hardware interface sort of, you know, talks to the hardware. You know, sends whatever language the hardware speaks. The hardware interface sort of both speaks that and also provides shared memory to controllers. And then the controllers come with are part of ROS2 control. And I think of those are more of, they're very mathy things. They're sort of mathematical objects. So like a PID controller or the forward command controller, or the trajectory, you know, like the trajectory controller, you could give it an endpoint. You just say, you know, 3 seconds from now, I want you to be at a particular endpoint. And then it does the math to figure out, okay, here's like a smooth trajectory that you could follow. I don't know if that's an explanation of ROS2 control. For our robot, really, so if you will, the controller, if you will, is running on the hardware, because the controller, the hardware can run really fast. I think it's like 10 kilohertz or something. Yeah, 10 kilohertz. And so really what we're doing here is we're just sending position goals to the hardware, and then the hardware is running the control loop.
Okay, and then what do you think? So how would you apply those from the controllers that you have shown to us? There are 2 different controllers. Yeah. One are the position controllers, and the other one is the trajectory controllers. So why there is the need to have both of them?
Well, I think the trajectory controller, as I was talking about a little bit, what Luca told us, is that the trajectory controller can guarantee that you're sending goals at nice even intervals. Whereas if you're using the position controller, then you sort of got, you're publishing to a topic, and then the position controller reads the topic and then moves the joint. So I think that I think a trajectory controller, you know, has the potential to be smoother, to be nicer to the hardware. But on the other hand, I was thinking about this, is that maybe for a walking robot, you want to be more adaptive. So potentially using the forward command controller could be better, because it would allow you to change your strategy, if you will, easier. I think, I mean, I feel like that neither one really solves the problem really well. I think ideally we would write a custom impedance controller that would give you that is again controls the reaction force with the ground, and also but then you can because you write it inside ROS2 control, you can get nice even spacing between the different points. But
that it was you were using trying to create those controllers, impedance controllers, and then can you tell us about the problems that so finally there was no more time to develop the project, but can you tell us about the challenges that you were suffering in order to develop the impedance controllers?
I mean, I was just trying to test it out in theory and simulation. So I was using, I think I just set up like an effort controller. And then the idea would be that you would just publish, motor currents. I would do the math inside a node and then just publish effort. And I ran it, and I would just say like try to go to different positions, and the impedance controller would just wiggle all over the place. So I wasn't even sure that I got the math right in simulation, like even the math right before like I could then even bother with doing it inside of ROS2 control.
Okay, and then one question here about the walking. That is about, so in the setup that you show us, even with the real robot, so you were executing your code in the cloud, right? And it was then communicating your instructions to the robot, right? So your code was not executed in the, oh no, sorry. So first clarify about that. So where are the controllers being executed in this setup that you show us?
Okay. So as I said, the hardware, there's an encoder on the robot, mm-hmm. and there's a motor on the robot. Mm-hmm. And the hardware, there's a hardware controller there that closes the loop. Mm-hmm. Right. So if you send the hardware a position goal, it will do that. And so really what we're doing with ROS2 control for us is really just say, here we have a topic on one end, you send something to a topic, and then the topic spits it out to the hardware.
Okay.
I guess, but here, sort of what I think you would say is that the references were being computed in the cloud.
Yeah.
So like you would read the slider in the cloud.
Yeah.
And then you go from the web page, it talks to the ROS bridge, and then the ROS bridge, publishes to the topic. Mm-hmm. So I guess in a sense, you have the latency of the cloud of the reference. There's latency in the reference, but there's no, like it's not affecting your feedback loop in the hardware.
Because the controllers, they are executed. I mean, the ROS control is in the computer that is attached to the robot. Then the final PID controller is on board the robot itself, right? But the positions that you decide into the different joints is sent from the cloud, right?
Yeah.
Well, in this case, it's not, because even you launch the web page from within the computer by using the Docker, right?
I mean, but then my computer is connecting to that web page. Mm-hmm.
Mm-hmm. Okay, so your computer is connecting to the web page, but it's only for the. Okay. So it's been displayed on your own computer.
Yes.
Okay. Okay. So the signal has to travel from your computer, from your web page into the robot computer. Okay. Then, so how do you think that it would affect this to develop? Do you think that it would be possible, based on your experience? Of course, it's your opinion about that. Is about developing a working controller for this quadruped remotely. So you have for example, in the cloud, you have the system that is computing the different positions for the joints in order to make the robot work. And then it has to send this to the ROS2 controller, which is on the computer attached beside the robot, right? So what do you think?
I guess. I mean, I think you're hinting at no, but I'm going to argue that maybe you could if you. I think sort of like you could. What you would do is you would make your web page, publish very high level commands like go forward, go left, go right, and then you would have a ROS2 controller, a ROS2 controller that handled more of the intricacies of walking. So I guess maybe the analogy I might be is, like if you had a differential drive robot, you could put a differential drive controller, in ROS running on the robot, and then you could have a web interface that sent commands to that, and you might be okay.
Yeah. So then that means that the actual working gate will be implemented in the computer that is running the ROS to control. Yeah,
I think so.
Yeah. Well.
I
depending.
Yeah, I don't think sending a walking gate, at least point by point over the web, is a good idea.
Yes. Maybe with a quadruped it can work because it's very stable. Unless you do some stupid things, but it's quite stable, so it's difficult to fall, but maybe we'll be doing something a little bit strange. Yeah, but it's good, it's good. We have a question here, says, can we see an RQT graph of the nodes involved in order to see the big picture? The ROS2 nodes.
There really aren't a lot of nodes. There's really just the ROS2 control node, I think. I'm not sure how good the graphic is going to be on the
just one node, right?
Computer.
Yeah, just one node. Then, okay. So let me see more questions here. So so forget about the RQT graph now. Then, how was the experience and the challenges of working with the low-level libraries? So what happened while you were designing these controllers? Well, actually, you were refurbishing, let's say, so modifying existing controllers for a similar robot, but it's a biped, and then adapting this for this specific quadruped, which has similar architecture, right? But it didn't work off the shelf.
Not really, no. It was a mess.
It was a mess, exactly. And that's where you started to be working with the low-level libraries. What do they do, those low-level libraries?
Okay. So there's sort of two levels of libraries. Shoot, I'm forgetting what there's a masterboard library. So the hardware of one of these things is you have your computer, the computer, which then has Ethernet, which talks to something called a masterboard. And then the masterboard talks to six different motor driver boards. Each motor driver controls two motors. And so, so then there's code that runs on there's masterboard code, and then there's also on top of the masterboard code they have they call the ODRI control interface, which is a level higher of abstraction, and that considers the point that these aren't just motors with encoders hooked up to them; they're joints. And so I guess just part of the experience was going through all that code and reading it and trying to understand it. And as I said, I think I found that business with the YAML file, which is a little bit of a bug. And so I guess you just look through it until you understand it. I didn't really look much at any of the code that runs like really low level stuff, like the code that runs on the motor driver boards, too closely.
And about this error, this bug that you found, have you considered contributing this improvement to the official project repository? Because it should be also affecting to the original project, right?
Yeah, I think this is I think that would be a good idea.
Okay. So
at least the spirit of, I think we can all agree that the joint shouldn't, the way the thing works might be a little counterintuitive. The way I solved it might not be the most optimal way, but I think we should at least let them know at some point.
Yeah. Okay, then please consider doing a pull request to the original repo. This is like homework after you have published this, because you are going to learn and practice how to do a pull request to an existing project, it's very convenient for your own career, because you are going to need to do that. Well, because it's fair, because you have used a lot of what they have done, so they deserve that. And second is because it's going to make you practice this thing that is going to be very common along your career. Okay. And I think that I have asked all the questions that were requested here. Anything else, Alberto?
No, I think it's enough. We have tested already Steven quite well in what he has learned with this project. So yeah.
Okay, so thank you very much, Steven.
Yeah, thank you.
And sorry for the inconveniences.
No worries.
Okay, so now.
So now we are going with the second presentation of today, which is going to be done by Olumide Godson. Let me remind it very quickly. Yes, okay, yeah, I agree. Let's do a very short break, and we'll be back in a couple of minutes.
Yes, counting here.
All right. Hello, hello. We are back. We have here Olumide, who is ready to the presentation. So let's go with him, and yeah, let's hope that everything is okay now. Give me 1 second.
Olumide, you are muted.
Yeah, please unmute yourself. Okay, yeah, now we hear you. Okay, so let's go with Olumide then.
You can hear me? I can hear you. Can you hear me? Sorry, you say you can hear me? Oh, okay, cool. Thanks. All right, so my project, wait, I feel like I'm hearing myself echo. You hear? Hello, can you hear me? Okay, I was hearing like a lot of echo in the, I was hearing a lot of echo in the background, so. No, I don't hear it right now. Just previously, I could hear like a lot of background. Okay, I'm sharing my. Can you hear me still? Because I don't know, I can't hear anything now, so I'm not sure. Oh, sorry, my fault. All right, so my project was basically an RGBD system. Well, we started off as a stereo system, but then the robot we had in simulation, the RB1 robot uses RGBD camera, so then it got converted to that instead. The goal of the project essentially is to localize and map an indoor environment, which is where the benefits of using an RGBD camera comes from, because you can get the depth information without having to worry about initialization issues that would happen in the case of a stereo camera or in the case of a monocular camera. So just a brief description of how RGBD cameras work. They essentially work the same way as a laser. Well, the newer ones work essentially the same as a laser. They emit a light beam to a target object, and then based on either the structure of the light that comes back or the time of flight is what's used to determine the distance of that particular point. it does have some limitations. It requires a lot of power in comparison to other methods, that is. And it also runs the slowest, in my case anyways, just because there's a lot of processing of point clouds before you can actually get to the SLAM system, which I did. I did a bit of a test with the stereo cameras. It took about 0.05 seconds per cycle, which is pretty quick, and we work real time in terms of outdoor. And in the RGBD case, it was 0.1 seconds per cycle, which in reality will get you killed if you're relying on it. So there are reasons why this could happen. It could be the system itself. Also, like I mentioned, I'm directly using the point cloud to get the distance. An alternative would have been to use a depth image, but during testing, it was the image was inconsistent, so I couldn't run a proper test for this project. So for this presentation, we are using an RGB image and a point cloud, just to be clear. So this is the overall setup. There's the input section, which gets your RGBD image and gets your point cloud. There's the front end section that uses orb features, and also we randomly display points through an environment. We extract the depth from the point cloud, based on the features that we selected. And then we perform odometry, which is a lot of math. This then goes into a map viewer, which shows your current position, as well as it gives you point cloud information on the features it's picked up in your environment. And then afterwards, there's an update system that takes a history of information to optimize for your current position. So optimize the pose and optimize the pose of the features as well. Might be a bit confusing right now, but I'll show a demonstration in a bit. So I didn't start from scratch. I had a boilerplate, what's it called? I had a boilerplate code, but I made improvements on each step, I would say, and we're able to reduce the root mean squared error from about 15% to 6.7%, which is pretty cool, considering there are other things you could do. There are other additional things to do to improve. So this score could be reduced quite a bit. One of the improvements I made was, in addition to using features that were gotten by an orb descriptor, I randomly selected points based on gradient information. The reason for filtering on gradient information is to reduce the number of points, because again, power consumption and runtime efficiency. Also, we sampled points based on a radius, so points are not too clustered together. This just allows to reduce for redundant calculations later on. And then we used a lot of outlier rejection. So we use ransack, we use interquartile range, and essentially this benefits the program in two ways. One, it reduces the memory overhead. We're able to save by 5%, and it increases your accuracy, which is part of the reasons why we're able to drop down about 9% in total. It does lead to a 1% increase in cycle time, but that's really negligible considering everything else. There's a backend sequence. There's a backend sequence which uses a pose graph. I'm not really sure how to explain this, but essentially it's records your information per time step in a graph manner. And between each time steps, every information you can get. So camera data, IMU measurements, LiDAR measurements, GPS coordinates are recorded, and then that's what's used in the calculation. If you want more information about it, there's a YouTube link here, which basically talks about a pose graph in detail. Here are the main nodes that are working in ROS. There's a controller node, and then there is the reader node, which again works in the input section, as mentioned above, and it transfers camera, image, and depth information to the front-end node, which estimates the current pose, and then we display it with the viewer node. So at this point, I'm going to show a little presentation, a demonstration, sorry. I can hear you. Can you hear me? Okay, so basically, I just launched the ROS bridge, which transforms the topics from ROS 1 to ROS 2 topics. And then I launched the environment, which is this guy over here. Hope that's clear. And I'm launching the code for the system, the SLAM system, which the results are seen on this frame. And then I'm launching a Téllez so we can move the robots around the environment. On this screen, you can see three things. Here's an RViz pop-up, and it's going to show the original, the ground truth, and it would show the estimated pose, estimated trajectory. On this side, I'm not sure if it's big enough. It's not getting bigger. But this essentially shows the tracked features in the current image, all of it. And then this screen here shows what we're actually using from previous images. So to run, the ground truth is in pinkish type situation, and the predicted is the blue one that's in the environment. As you can see, the images are changing based on how we're moving, and the detected points are also changing. I'll let it go for a little bit and stop. Oh. So right here, we've run into one of, sorry, can you hear me? Hello? Oh, just because it's lagging, so I'm not sure. I'm not sure exactly where I am. Okay, so run a load simulation, and as you can see right here, we're no longer predicting the pose, the current pose. It stopped in this case, and we run into a failure case. This is one of the current limitations of this. It's one of the current limitations of using this method with just the cameras. Because we're using cameras and cameras cannot capture high-speed motion. Well, this camera can capture high-speed motion. It's also an event camera. It limits your speed to a ridiculously low rate. I'll show in the end one that's working completely. And it also doesn't perform well in pure rotation. Also, as with all things, it's a sensor. It's not an accurate, sensors have variances in their readings. So over time, there is drift. This current method right now doesn't include anything to account for drift over a long period of time. So loop closure will be a way to account for that, where when you go around an environment, if you see a place twice, it would optimize your history of poses and features based on that information. So you do like a global map update. So this is one of the things that I'm looking forward to working on later on. I'm going to add a loop closure system. And what it does is, like I said, when you recognize you've been to a place multiple times, it checks to see if there's actually a loop detected. So if this is actually somewhere we've been twice, and then it corrects, and then it optimizes globally everywhere we've been to, including our current position. The methods for loop closure right now or the main method is a bag of word method, in which you take images of your environment and then you describe it using histograms. But the issue with that method is it doesn't work real time really, and you can't update it in real time. So it requires you to have prior knowledge of your environment. So say you were in a house situation, you'd have to take pictures of everywhere in the house before you could use it, which kind of limits its usability somewhat. For LiDARs and other forms of sensor of measurements calculations, you can actually do real time, because you can update the dictionary information as you go. So to that end, I sort of started working on a potential fix for this, for the visual case. We could turn 2D orb features into 3D features in a sense. When you use an orb descriptor, it returns a 32 length vector for each point that it sees. What we could do is, when you're given a point, you could take a circular, you could take like a circular view of it based on a particular radius that will be used to determine, and you can split it into 32 sections. And then what you do is, in each sector, you take the closest point to it, and it will give you a distance measurement. So in this case, you would have an orb feature that has a vector of 32 length, and you would take a point, look at the surrounding points around it, and come up with a vector that's also of 32 length, but then it will represent the closest distance to the current point based on an angle view. And then using the cross product, which I sort of tried to explain here, using the cross product of this distance descriptor, which I'll call it, and the ob descriptor, you can get an overall point descriptor that you can then use to update your, you can then use to do your loop closure, sort of in the 3D sense, like it's been done with lasers and IMUs and stuff. So this is the end of that presentation of this, just the description. And I'm going to run a simulation that actually works. I just have to restart the environment, so everything goes. You still with me? Did I lose anyone?
Everything good here, yeah.
Okay, cool. So launching gazebo, launching the Ross Bridge. Then launching the project. One second, reduce this. Okay. So like I mentioned earlier, we can't use high speed. So we reduce this down to about that much, and also reduce the angular speed. Also reduce the angular speed, and then in theory, you should see a track better. So this is the ground truth in pink here, and then the, oh, sorry. Where am I? Yeah, this is the predicted odometry reading, and the ground truth is in pink. I don't know what's happening. What is happening? Sorry, 1 second. Give me 1 second, please.
Yeah, don't worry. So have you changed a parameter there?
Yeah, so these are just parameters that sort of affect how it runs. This is to show the point cloud, so control the loop, so control the flow frames per second, and then maximum, minimum camera parameters, so your maximum depth, your minimum depth, an image draw, just again for memory management to know how many images we're currently tracking in total. And then these are for your ob features.
And which are the ones that you were suspecting that maybe were wrong?
I'm thinking the image draw.
Okay.
But let me see. just had it set up right now. Think in the image trail. This is T. Okay. Now we're predicting. So yeah, the image trail was the issue. Basically, I was trying to, after we only tracked 20 images and then it stops. So if I make the image trail longer, then this would be less of an issue. So just bear with me 1 second. Trail, let's make it. Yeah, so there's a real difficult balance between the number of images we keep in stock and the predictor, just because I'm not sure, but it's not running quite fast enough.
So just to make it clear, so you mentioned before that these pink dots are the real odometry, and the light blue ones are the predicted, right?
The light blue ones are the predicted, and the pink one is the actual, so the ground truth.
So what should we be seeing here if it works correctly, and why this is not the expected thing?
Well, if it works currently, you should see this purple thing sort of dance around the straight line.
Mm-hmm.
So it's not exact, but it dances around the straight line.
Mm-hmm.
As for why it's not, I'm going to look for a previous setup that I had, and let's see if that works. So it's something to do with the configuration. You can keep a long list of previous images, but then that slows down your runtime drastically. Or you could, reduce that trail and then not get accurate results. So I'm just trying to find a previous setup that I'd used and then see.
Maybe you have a video recorded or something that we can see?
Did not record the video, probably should have done that. 1 second. Please bear with me somewhat.
Yeah, so at some point there in RVs, we can see that the predictions stop arriving, right? That shouldn't be happening, I suppose.
But that should not be happening. Okay. And try this again. So it's hitting a state where we're not getting any images, and that's why it stopped. Right. Okay.
Can you plot the images on Arbis? So we are sure that the images are being published.
Sorry, repeat what you said?
So yeah, so at the same time that you are visualizing the odometry, can you add also a display to Arbis so we can see that the images are being published?
So for some reason, Arbis doesn't consistently publish compressed images. One second. Just need to do that again. Okay. Okay, this is a different version. Okay, sorry. This is great. Let's do this. So these are the images. Ricardo, you're asking for images to be sure that it's viewing?
Yes. So
yeah.
you can see that the images, so if you move the robot, those images, they should upgrade, I mean, change with the movement. So if we can see that, no, but that's not on Arbis. Those images those are not Arbis visualizers, right? Those are your own visualizers.
It's OpenCV visualizers. I said, Arbis. Okay, there's an alternative.
No, I was just suggesting you to do that on Arbis because then you can be sure that the robot is publishing the images. If they appear on Arbis, and then you can see they changing as the robot moves, then it means the simulation is correct. So you don't have to kill it. Or RQT view also you can do. Yeah, that's the same because it's subscribing to the topic. Yeah.
Is that what it's called?
I think it's the opposite. It's RQT image view.
Image view.
Image view.
Yeah.
Thank you. So where are we? Over here. So yes, it's subscribing to the topics. This is this is showing the match features, and this is showing what's detected in the environment.
Okay. Yeah, but again, you are still showing the production of your program. Okay, so you still are not. That's very good. Okay, so if everything works, that's perfect. But in case that is not working, then you need to have a method for finding where in the whole sequence of things you have the gazebo, the bridge, then your program. So you have to figure out at which point your images are getting lost, right?
Yeah, so what I'm saying currently, this topic, I'm publishing this topic. This is a topic that I'm publishing.
Okay.
It takes in it reads the environment, and then we put points up showing what we're tracking currently. So that this is working means the system is working, is what I'm saying.
Okay, great. Then go ahead. Perfect.
All right.
Let's have a look then.
So hopefully third time is the charm. And then if we move. Okay, there we go. So the blue line shows your current predicted odometry. Can you see that?
Yes.
And the red line shows, why isn't it showing the actual anymore? I'm not sure why this isn't showing the actual odometry anymore.
Yes, it's
appearing there.
Yeah, but it has missed the previous publish, so that's why they don't appear.
Okay, it's back again. So here is both of them running, essentially. This is going to carry on until we hit a place where we can't spot any features. So I'll stop it here. I'll rotate a little bit. Okay, rotate. Move. Rotate them. So you can see it here. So trying to track what's going on. But like I mentioned, we're limited by a couple of things. One, we're limited by speed, and we're limited with speed of the vehicle moving, and also programming speed. So the software that it's on, the efficiency of the computer that it's on. Because on a different PC that's a bit faster, it will run quicker than what's currently running at. Like right now, it's running at 2 seconds per clip. 2 seconds per clip. On a much faster computer, it would run at half of that. Last thing I wanted to show is, although this is not really useful in this case because this is a depth camera, so it shows the point cloud. We could, I'm just going to restart the environment, but we could also, using this method, show point clouds map your environments, essentially, if I'm going. One second, just have to activate that. So the image throw was the issue from before. I had too much, so I wasn't tracking properly, and then I had too little, so I wasn't. It seems there's like a sweet spot between 15 and 20 that makes it work. So that's where we're at currently. I'm also going to launch everything again. And then in this case, based on features that we're detecting, here, can you see that?
Yes.
So based on the features they're detecting in this image, we are producing point clouds. So if we really look at it, this right here is representing the first cone. One second. Come on. So this right here is representing the first cone. You can also see the second cone. And then if we move around the environment, it updates, but this also makes it that much slower. So it's not going to run real time, really. So as we're moving, it moves, and it's so recalculating and updating as we go through the environment. But here we go. So yeah, just wanted to show that as well. The other things that we were required to do for this was to get a web page going. And also a Docker file. I do have a Docker file. It's not updated. It's not uploaded to the hub yet. I wasn't sure that's what we're supposed to do. And in terms of the web page, I did start it, but I had some issues yesterday. So connecting with the Rust bridge, but essentially this shows boilerplate for the entry page. And then this is where it would have been displayed. So the two images that you were seeing before would be on here. And then this would have been the joystick to sort of control the movements and that. So that's pretty much the end of it.
Okay, so thank you very much, Olumide.
Yeah, so let's go with the Q&A session. So we have some questions to make. Maybe I can start myself. So because I'm curious, I'm very curious on. So you have created your code in ROS 2, I can see, but then you are using a simulation in ROS 1, and because of that you have to use the ROS 1 bridge. So if your code is in ROS 2, why didn't you go for making just everything work in ROS 2 and don't have this?
I heard the last part what you said.
Yeah, so why you didn't choose to make just everything in ROS 2 and have this kind of hybrid with simulation in ROS 1, your code in ROS 2, and the bridge in between, and so on?
No reason in particular. Just the simulation. I didn't want to focus on simulation. I was just focused on the code itself, and basically, I just didn't have enough time to get to making everything ROS 2 based. But the bridge was working fine. It didn't give me too many issues. The only thing that was giving me issues was really finding the configuration that works, because it's so configuration sensitive. So it wasn't really a small bother. Also, really, most things that most Rust packages currently are ROS 1 based. So most environments are ROS 1 based. So it's just an easy plug for anyone to use, which was the idea initially.
Okay, can we ask you, Olumide, to activate your camera so that we can see, because otherwise it's a little bit strange here.
Activate my camera?
Yeah, so that we can see you and...
Oh, okay. Oh, I thought it was on the entire time. Oh, my fault.
No, you were showing your desktop.
Oh, sorry about that.
Oh, there it is.
Okay.
Hi, people.
Still, I mean,
I think that saved me. You didn't see me when I was panicking.
Okay, and then I think that some of the teachers didn't get the role of the ROS bags in your programming. So because you have been showing how your software, how your algorithm works from the simulation, but they are asking about why you didn't use a ROS bag. I think that you didn't put it clear, the role of a ROS bag.
A ROS bag?
Yes. A ROS log file containing data recorded from the simulation.
Yeah, so there's a space limit on the Rust jet. I did have a Rust bag, but when you record the RGB image and the point cloud alone, in about 2 seconds, it grows larger than the space I'm allowed to have. So because of that, I just didn't bother with it. So it's more of a space limitation thing on the Rust jet.
Okay. Yeah, because the question is very good, because that's the usual procedure, is to start by, instead of using the simulation or the real robot, so we record the ROS back and then you can start using this. But you actually use the log file containing data at the beginning while you were developing your algorithm, isn't it?
Yeah, I usually at the beginning when I was developing, because I was having some issues with the compressed image. For some reason, I figured out the reason afterwards, but initially, the compressed images, either the RGB image or the depth image, were not coming in consistently. So to develop, I used the raw images initially, but then after a while, I'm doing some research, I saw I had to update. I had to do a ROS update, and when I did that, then I could go back to, I didn't need to use the ROS bag anymore, just because, again, the space limits. And also, this project uses a lot of third-party files, so I had to install new OpenCV, I had to install G2O, I had to install so many other libraries that it was just becoming a hassle. Like right now, it's at 4.3 gigabytes, and that's before actually installing other things as well. So just to save space and to be able to maintain within the Rust jet is why I don't have a Rust bag in here currently.
Okay. Then,
But with the current configurations that I put in, it should work regardless. Just initially I was messing about prior to presenting. I thought it'd be cool to show a field case and then show an actual running case, but I kind of didn't go as planned. So,
okay, but then for the next project in which you work, please use the ROS bag. So
next project I'll use a ROS bag for sure. It's just against space limitations here. Yeah. That was the hindrance.
And then questions about the difference between an RGBD image. What is the difference between an RGBD image and an RGB plus point cloud? So is there any difference? So you use a topic like image row and points and combine them? So how did you manage this? Why all these complicated things required?
So what you need to be able to estimate your location is you need an image that has the background, but then you also need to be able to extract depth information. In stereo camera, you use 2 images, so you subscribe to 2 image topics, and then you triangulate and you get the depth. Mm-hmm. For a depth camera, it usually would come with an RGB camera and an RGB image and a depth image. So from the depth image, you can calculate your distance for each pixel. Mm-hmm. Or in this case, you'd have an RGB image and a point cloud.
Separately into topics.
In 2 different topics. Uh-huh. So that's where the RGB image will give you, the view of the environment. Mm-hmm. And then based on your pixel location, you can then calculate your distance
from the
point cloud.
From the point cloud topic, from the other topic.
From the point cloud topic.
But you have to do kind of correspondence.
Yeah, you have to do a correspondence. So what I did was I just took everything as a 1D vector. Mm-hmm. And then when I knew my pixel location, I used that to also know my where exactly in the array I had to go to. So it's just about matching 1D locations at that point.
Okay.
Yeah.
Okay. Yeah. So there are also another question that I think is interesting is, So, what is the purpose of this localization system? I mean, why would someone use this kind of localization, your package, the one that you have designed, and how it compares to other localization systems? Like there already exist others like ORB SLAM, deep learning localization methods. So how it is better, how it compares to those ones?
So I can't really do a good comparison because I haven't tested that far in. Right now, this was more of a fun project or something that I've been sort of studying up on and reading and working on. We did have we had a base code to compare with, so that's really all I can do the comparison with. And right now is just more of a proof of concept. Well, ideally, this is a proof of concept that with the same base code, if you add a bunch of optimizers and you do some clever programming, you can reduce the error measurement. Because nowadays the goal is either buy more expensive sensors that be more accurate, or use a bigger PC or whatever. But in this case, I was just more trying to compare it to a base case and then from there. Going forward, though, I don't think this is something anyone should use currently, because again, it was just a fun passion project I'm working on. But there's a lot of things to improve on. Like someone had mentioned the deep learning aspects of it. You could just swap out, instead of using all features, which really is here and there, it's human engineered. You could swap that out for something like deep learning, in which you get better feature representation. And that helps your loop closure system work better, because now you have something that's a bit more descriptive than an orb feature. Or, in here, I'm using basic methods, essentially. I'm not doing, my goal here was to see the effect of outlier rejection. That was my personal goal, to see the effect of outlier rejection on a system as a whole. There are things like inverse depth parameterization that you could do. There's things like structureless optimization, which will make you run faster as well. So right now, this is just a fun passion project. Nothing that anyone should take and hop into just yet. But in a couple months, because I'm looking to carry on this project, then it could be something that could be used generally.
Okay, let me ask you about the loop closure. So what is the purpose of the loop closure? And how does it improve the localization? Because loop closure, usually it is used on systems where you have a robot that is moving in a big environment, let's say, and then it goes through one side and then kind of comes back to the same room, but from another side. And then it identifies this place as that's the same place as I started, for example. So in your case, you are moving the robot just in straight line. So loop closure, it looks like it should not be necessary in that case. So how it is necessary?
Yeah, but this isn't supposed to work in a straight line. This is supposed to work in wherever you wanted it to. It's just two things. One, I ran the initial code on my personal PC, which is a lot. It's a modern PC. There's a lot more cores. So doing things like multiprocessing and all of that, it was way quicker than on here. After putting it to ROS and seeing how limited the processing power was when I reduced my scope to let's go straight line and one turn. And then I could show the effectiveness of that. Loop closure, you're right. If you're going just in one direction, doesn't help. But the idea of this SLAM project is not to be in, just a one-trick pony, is to be able to explore various environments as a whole. So that's where, in this particular use case that I just showed, it's not really effective. Except, like you said, I go back to the beginning. But for example, if you're coming back and it's the same area, It doesn't have to go exactly back to the beginning. It just has to be a similar
Exactly.
similar area.
Yeah.
So using that, then you can update. So, you know, it kind of goes straight, then make a right turn. If you make another right turn while you're going back up, it could update all the previous poses based on a similarity threshold that you're given. So that's where it would be really effective and really useful.
Okay. And one question is about the nodes that you are using. Can you show us the nodes that are actually running with an RQT graph?
Then show an RQT graph. I could just show right here because this is very much.
But we want to see the ones that are running.
Yeah.
The run.
Are you seeing my current screen?
Yes. But we want to see it live, like running.
Oh, live.
If it's possible, if it is possible.
1 second, I can pull it.
I think that you have everything launched, if I remember properly.
I don't think the code's running. Yeah, the code's not running. No, the code's not running.
And the bridge neither.
Yeah, and the bridge.
It's because in your case, it's going to be, should have a few nodes there running. So it's going to be very interesting to see.
It's just 3 nodes.
RQT, graph, RQT.
Where did we go?
Yes.
So, essentially, that's the spread.
Okay, I don't understand. So
We
how
have the
this translate to your nodes?
So basically, I'm only running one node because I'm using components.
Okay.
So they're all within the visual odometry container.
Okay, now makes sense. That's what was the next question. So you also answered now. Okay, great.
Yeah, so in the components, there are 3 or 4 nodes. Sorry, one second. Nope, wrong one. In the component, launch file. There we go. In the components, there is 4 nodes. The viewer node is just the main one, so the parent that controls everything.
Mm-hmm.
Then there is the visual odom node, is the one that controls everything. Then it's the reader that connects your environment to your system. It just reads the sensor information from the camera. Then there's the front end node that does the initial pose estimation. The backend was not implemented as a node because it doesn't directly use anything Rust related. So it's just a single thread that runs by itself. And then there's the viewer node for publishing topics. So the images we saw previously that showed the detected images and the transition images. Because then that was going to then link to the web page and then you'd see it that way. But I couldn't get to that, unfortunately.
Okay. And about the markers that you are publishing, so how are you doing that?
About the markers?
Yes, the markers that you are publishing that are indicating the odometry. So you are publishing that, right? The blue, the green color, and the red, the ground truth, and you computed one.
Yeah, so it's just we're publishing. Well, the odometry topic is always publishing, and then I was publishing a predicted topic.
And which type of message are you publishing in there?
It's just
also an odometry?
Regular. Yeah, just an odometry
message. Oh, okay. Odometry message or pose?
It's a odometry. Well, it's really a pose message, but it's inside the odometry message because I was going to try and get the twist as well, but I couldn't get to that either. So it's just two it's an odometry, it's a navigation message
Mm-hmm.
and 2 compressed image messages.
Okay.
So the compressed image messages are showing what features we're actually focusing on and what features we're trying to use as well.
Okay. Let me ask you one final question because we have to finish now. So, what about the features? Because it looks like this simulation was kind of poor in terms of features. So, would that adding objects improve the performance of your code?
Doesn't necessarily have to be objects. It's just more textures in an environment because the way the features are really is doing a local gradient search, and then if you get past a certain threshold, then it's accepted as a feature. So things like things that have corners or things that have edges. So really, a textured wall or even just a rug would make a difference because it has a lot of textures to it, which is where deep learning could be a benefit because it's not, I mean, depending on how you do it, it's not going to be solely texture based. So having more features could be better. But what I tried to do to compensate for that was I used, because when you use orb, it's only going to take things that it really thinks are features, like things that are really corners or things that are really edges. It doesn't take random points. So I included random points that have a really high gradient threshold. So like 0.7 threshold, bigger than that. And then I'm using that as well to calculate, which is one of the things that helped reduce the error in comparison to the boilerplate code, because the boilerplate code had 15% error. And this ended up having 7.5% error when I tested it on a different data set. So on the Kitty data set. So it would help having more, but I think I'm already sort of accounting for that by using high gradient textures. I mean, high gradient image points as well, because then I'm not so reliant on orb features only.
Well, do you think that it would have been easier? Do you think that it would have been easier because you will have more, by having more textures, you will have more points detected, right?
Yeah, it would. It would have been better for the matching between images. Yes, it would have been better, and then that would make it. But I'm not sure exactly how much better because I haven't tested it, so I can't say for sure.
Yes, then this is a bias for your next works when you go to work in another company or so on. So try to put it easier to yourself. You know, so you can put a lot of textures, so a lot, even if it is not realistic, but you can put a lot so you can improve your algorithm in a, let's say, in a very good situation, and then you can debug a lot of stuff in a good situation. And then afterwards, when everything is working, then you can start removing those features, for example.
I feel like there's pros and cons to that.
Yeah.
The pro is obviously it's going to work really well because you're in a textured environment. Mm-hmm. But I feel like that will give you that's what gives a false feedback, because I think if I started with something that had a lot of textures, I wouldn't have thought, okay, if I try to take out more outliers, what does that help? Does that actually do anything? Or if I try to include random points, does that help? Does that actually do anything? So I'm not against it, but I'm saying like this method also works, because really, if it works relatively okay, because like you could see the blue point it wasn't bang on, but it was dancing around. Mm-hmm. And the only place you had an issue was when it was pure rotation. Mm-hmm. But camera systems generally have an issue in pure rotation, which is why they use additional sensors. Right?
Okay.
So.
Yeah. Okay. It was just a suggestion.
No, I'm agreeing.
Okay.
I'm agreeing.
Great.
I'm not agreeing. I'm agreeing. Great. I'm just saying, like, there's other factors to it as well. Okay. So.
Then, what else?
I think more questions or
No, it's okay because
it's okay. Okay, yeah.
we already have been 1 hour.
Okay, yeah.
Already. So
Yeah. So then, so let's leave it here. Let's give Olumide's presentation for finish it. Thanks a lot for your presentation.
thank you. Thank you.
And so now I think that we might get a 1.5 minute break.
Yes.
Only just to get some strength regained.
And then
So
we come back with.
and then we are going to come back with the final presentation of today, which is Jason's.
Hello, can you hear me? Il peut me voir. Can someone hear me?
All right, so we are back here. Jason is ready to start his presentation. So yeah, I will leave you directly with him. Go on, Jason.
But unmute first.
Yeah. Please unmute yourself.
I think he cannot hear us.
Hello, Jason. Can you hear us?
No, definitely not.
Jason, hello. Yeah, apparently not.
It's not. Maybe you one of those you muted.
Yeah, no, because it's
There. Yeah. So.
hello, Jason.
Hello, Alberto.
I can hear you. Can you hear me?
Hear me now?
Yes, I can hear you.
He cannot hear us. Do you have the headphones? Because I don't know. Let's see.
So I cannot hear you.
Hello.
Hello.
Jason. No?
Can someone hear me?
Okay, so it looks like we have again some technical problems.
Relaunch the Zoom.
No, but so now is Jason who cannot hear us. So I suspect that everybody is hearing us on the streaming. So it looks like something on his side which is not working.
Yeah.
Let's see if he can come in again. In the meantime, some musical minutes.
Can you hear me?
Hello, Jason.
No, he doesn't hear us.
Not yet.
Okay. So then we'll need more musical minutes.
Hear anyone?
Hello.
I think.
Hello.
Okay. Let's do a hangout directly here with him. So do you have his? Please call him on the screen. Call him. So then get him direct instructions. In the meantime, what else can I tell you? So I think that another thing that I can tell you. Let me.
Hello, Jason.
Please call him with a hangout. Then in the meantime, let me show you, for example, here about this master, where those students, they are now presenting. They started this master on February. So on February, and then let me show you on the screen this webpage where you can get more details about this master, just in case that you are interested. It's about a 6-month program. I'm searching for the webpage, okay? It's we call a MasterClass And you are going to learn from starting from zero how to become a robotics developer. So I'm going to share my screen with you now, and let me see if I can do it now. So in order to show this, I'm going to show
You can hear me now?
one of the applications now. It's just go and do it in another place, and then I'm going to show you here the information. So now you can see my screen. And this is information about the master class, that it's in order to become a robotics developer in only 6 months. And you start from zero. It's the next batch is going to start on January of the next year. And the format is completely online. So you are working with simulated robots in your place, at your place. And you are also practicing with our robots, which are here in Barcelona, where we are located, and you connect remotely and you use the robot. You have seen on the first presentation, Steven, how he was using the quadruped. Even if you can see that the quadruped was hanged there, it's because that quadruped has been received very early, just some months ago, and still there are no controllers for it to make it work. So in order to develop the first ROS2 controllers for this robot, it has to be hanged so the student can practice without any problem that the robot falls or breaks something. But that's one case. Then in the case of Olumide, he was using the simulation, but the same exact environment that Olumide shown on the simulation, it exists here. It's the same robot, the same room, the same objects in here, and then you have to connect to those robots. And as you can see here in this image, for example. So the program is 100% online. You don't need experience. We are going to teach you about the basics of programming also from the very beginning with Python and C++, and then we teach you many subjects related to robotics development. So how to program, that's one of the first things. And then how to program with ROS, it's another thing. And then we are teaching you about how to do everything with ROS, first in ROS 1 and then second on ROS 2. We are also including all the mathematical skills that you are going to need, for working with robots. So sometimes you need a mathematical background in that sense. So you are going to learn it about the kinematics and dynamics of the robots and how to compute that. For example, one of the examples of computation of the kinematics was the example that Steven on the first presentation he did for the quadruped, how to do path planning and so on. And then finally, we are including another section which is about DevOps for robotics, where you're going to learn all the development tools required to develop in a robotics environment. So if you go to a company to work programming for robots for that company, then you will need to know how to do unit testing, how to use Docker with the robot programs, how to use Git, how to use Jenkins for do a continuous integration system, and also how to program web interfaces for robots. So all that is included, and it's based on some lessons with practice with the simulation and then the projects where you have to apply this to the real robots, different robots that we have here in Barcelona, from mobile bases, robotic arms, and so on. Then have a look at this website where you can have more details and maybe download the detailed brochure for your information. Here you can see another example. This is our lab, the warehouse lab, where we have this robot, and that is the one that is being connected remotely by the students and getting the image, RBs, and so on. So you can have more details by visiting this. And also, let me tell you that we have an internship program in collaboration with some robotics companies around the world, where you can practice with your skills after everything is been finished, the master. Then you can go to the internships and apply what you have learned. Okay, so you can have a look at this on the website, and I think that we are.
Yeah.
Yes?
So, Jason, can you hear us now?
Wait a second.
Yes, I can hear you now.
Okay, great.
Solved my audio issue.
Okay,
Sorry for
okay.
that.
Yeah, so we solved the audio issue behind the scenes.
Okay.
So, yeah, let's get back. So you can start sharing your screen, Jason, and the audience is yours.
Perfect. Can you see my screen?
Yes.
Perfect. So, hello everyone. My name is Jason, and today I'll discuss about the development of an autonomous mobile manipulator in a GPS-denied environment. So this project presents the development of a low-cost, modular, and easy-to-manufacture autonomous robot called Kali. As you can see from the pictures, the system setup includes a 6 degrees of freedom scoreboard ER3 manipulator mounted on a four-wheeled skid-steer drive mobile robot. And the ROS melodic distribution was used for software developments. So the main goal here is to perform a fetch and carry task autonomously in an indoor environment where the robot has to pick up an object from a known location and deliver it into a new location. So we can break down my mission into smaller goals. The first one will be to spawn the robot model into the gazebo simulator. The second one will be the autonomous navigation. And finally, we'll discuss about the manipulation perception pipeline. So going back to the first goal, we basically launched the gazebo world and with the transformations, and I spawned the robot into the gazebo world, loading the controllers for the mobile parts and for the arm joints and also for the gripper. The first challenge that I've encountered here was once spawned, the robot was slowly drifting over time. To fix this, basically I had to change my inertias and my masses. So I've used some macros in the Ezquerro file, for faster debugging. I'll show you what I've done. So this is my Ezquerro file, and basically I've used this inertia calculator because I needed to tune my mass, and the inertia depends on this mass. So for faster debugging, I've used this Ezquerro, which is an inertia calculator. I also set the correct friction. So I've tuned my mu1, mu2 for the wheel links, and also the friction factor for the joints, wheel joints. The second step, the autonomous navigation, I used the NavFN algorithm for the global planner and the time elastic band for the local planner. I've also created a service server to allow multiple goal poses. So the challenge that I've encountered here was related to the to the local planner. So I first used the dynamic window approach as a local planner, but it wasn't really suited for the robot. Especially it wasn't handling narrow areas, and it wasn't doing any backward motion. which resulted into the robot getting stuck into recovery behavior. So to solve this, as I said, I used the TEB local planner. With this planner, I was able to generate backward motion and avoiding getting stuck, and also avoiding avoiding obstacle more efficiently. This planner, as you can see, you can see it here, you'll see it later, but it allows, it creates like car-like maneuvers. One of the interesting part of this planner is that it allows multiple planning trajectories at the same time, which results in an overall better performance for the local planner. The other challenge was to tune the TEB parameters. So basically it requires a lot of resource. So I had like a large computation burden, giving some map and control loop updates missed. So yes, to solve this, so first I used RQT reconfigure tool to configure the parameters during runtime for faster debugging. To allow a good navigation, I've set a low linear and angular velocities due to the complex environment, especially for narrow areas. Like I said, I've set also backward velocity, allowing car-like maneuvers. And I've set the robot model footprint to polygon to optimize the distance calculation. To solve for the computation resources, so I speed up the planning by decreasing the dimension and the resolution of the coast map. That helped, that basically did the job for reducing the computation time. I've also set the multiple parallel planning to false, and also decrease some weights, like for example, the acceleration limits. I've also run into another challenge was that once I was using navigation, my local planner was consistently detecting obstacles right in front of the robots, which was causing the failure to plan correctly. This was due to the laser that was detecting their phone wheels consistently. So it was detecting like obstacles consistently. To solve this, I had to change the position of the LiDAR in such a way that it doesn't affect the local coast map. Another solution that I could have done was to decrease the range of the laser. But for simplicity, I've just changed the position of the LiDAR. Now concerning the manipulation perception pipeline, first, the manipulation is handled using MoveIt, and the manipulator is mainly composed of two groups, so the arm and the gripper group. MoveIt can either control the robot arm using joint angle commands or end effector pose commands. The arm joints are controlled using the joint trajectory controller, and the gripper. Concerning the gripper, so it's composed of two fingers, as you can see, and I used a gazebo plugin to allow the second finger to mimic the first one, because the gripper and action controller is a controller for executing gripper command action for a 1 degree of freedom gripper. So that's why I had to use this mimic plugin. Concerning the gripper, I've also used another plugin to attach my object. Basically, I wanted to help the object being attached correctly and avoiding any slipping out from the gripper once it grasps my object. Then for the perception, I've implemented the surface perception package, which is a library for detecting surface and obstacles on top of their corresponding surfaces. So what it does, basically, it just extracts the position data from the robot to the arm. Sorry, it extracts the position data from the robot to the object. To extract this data more efficiently, I filtered the surface to detect by height, so that the algorithm only focus on my surface of interest instead of getting data that I'm not interested in. And finally, I will regroup those two important steps to get my manipulation perception pipeline. I basically use the perception data, which is the position from the graspable object to my robot. I use this data, as input for move it to control the arm using the end effector pose. So the challenge here was to find a planning solution efficiently, I would say. I had a hard time to determine the correct offsets and orientation for move it. I also had some difficulties tuning the goal position and orientation tolerances. So for this, I first created a new end effector frame for the fingers. Sorry, I placed this end effector frame between the fingers to minimize the offsets for the end effector goal pose and to allow more efficient testing debugging. I've also set a simple orientation pose. Then I've tuned some parameters for the arm group. So I've set the planning time to 30 seconds to give it more time for the algorithm to find a planning solution. I've also set my replanning parameter to true so that it allows the algorithm to replan to increase my chances of finding a planning solution. So now we're ready to present the simulation. I have a little video showing my simulation, but we'll do it in live together. Oh. I've actually launched it. I'm gonna launch from 0. So the first step is to spawn the robot into gazebo. So as you can see on the left, we have gazebo, our simulated world. And on the right side, I have RViz for visualization. So I'm gonna correct this so that you can have a better viewing. It requires quite a lot of resources, so that's why it's so slow. Bear with me. Then I'm going to launch the navigation. I will then launch my navigation service server. This will allow me to choose among different goal poses. Oops. So I'm trying to reconnecting gazebo, trying to zoom out a little bit. I'm having it. It's something is not correct here. I'm not sure why. My table is not. I'm not sure why. My table is not set it correctly. I'm gonna relaunch the simulation. Sorry. I'm not sure why this happened. Sometimes gazebo doesn't work correctly. Not sure why. So we're just gonna relaunch this.
Yeah, don't worry.
Simulation.
Gazebo always, yeah, always crashes in the better times.
In the in the most important times. Yeah. So I'm relaunching my simulation. I'm gonna directly check if everything is correct. Good. I'll zoom just to see if I have my object on the table, and I have it. I can see it. I'm not sure if you can, but I have my object.
Okay. Yeah, we see it.
Perfect. Okay. So I'm gonna relaunch the navigation node. And the service server. Okay. Now I'm ready to call my service. So basically, I'm gonna call the service to in order to go to the my position, my goal pose, which is close to the table. So in green, we can see the global planner, and in red, it's the local planner, the TEB local planner. Okay, now I'm gonna zoom to gazebo. Once it arrives close to the table, I will launch move it to orient the arm because the camera that I use is connected to the arm. So I don't know why there's a delay. So I'm gonna basically use move it to allow the camera to be oriented towards the table. So there's a little lag here, I'm not sure why. In Orviz it arrived, but in Gazebo it seems, oh, it's here.
Okay, now it refreshed. Yeah. So.
Yeah, it's taking a long time. On my local computer it works perfectly, but here I'm having some computation issues. So now, like we said, I'm gonna launch move it.
If it's going too slow, maybe I would suggest stopping navigation now, because otherwise...
Because I'm going to use navigation later again.
Yeah.
You have 3 RBSs there.
Maybe that's why.
Yeah. Close this one, for instance. You don't... no, not this one. This one is the moving one. But the other ones, you can close them.
I'm using navigation layer, that's why.
Okay, then the first one, maybe, you can close.
Which one?
The one which is opened with the simulation.
Harvest, which is
launched
with the simulation.
Oh, wait,
the graphical tools window.
Yeah.
The graphical tool window.
I'll give it a try.
Okay.
So now I'm going to orient the camera towards the table. I'm going to go back here. So we should see the arm move and orient towards the table. So it's executing. And we can see the output, which is the point cloud. So we can clearly see our table with our Coke can on top of it. Now I'm ready to launch my, so I took out the point cloud so that we can better understand what's happening next. I'm going to launch my perception pipeline using the surface detection. So normally we should see the perception. So we see it now. So it basically recognized the surface in purple and my object in green, my Coke can in green. Now, like we said, I'm going to try to extract the data that this algorithm is doing. So it's the data that I'm interested in is the position from the object to the Coke can. Sorry, the object to the arm. So this should return my position, my X and Y, and Z also, and the orientation. Okay, so now I'm going to launch my manipulation perception pipeline. This is the most challenging part of the project. So it takes a little time. It will first open the gripper. You see it open. And now we can see that the position from the table is 72 centimeters in this direction, in the X direction. And if I go into the Move It window, it's now planning, trying to find a planning solution. So it's doing the second attempt. And it found a solution. It's very slow. I don't know if you can see it. So it grabs the Coke can. Once it's grasped, I can launch my, so I'm going to close those two windows. I don't need them anymore. Now I'm going to use back my service server for the navigation to go back to the new goal pose where I will release my objects. Now if I go into navigation, yeah. So it's like we see, it's going to do like a car-like maneuver, like I was talking about. It's going backwards. going to zoom out the gazebo world. It's a little slow. Also, so it's during a maneuver. And finally, the last part will be to release the Coke can into a trash can. So it handles pretty efficiently narrow areas, as we can see. So this is my trash can here into the gazebo world. You can see that I detect it in the RVs. So this part is trying to find the perfect. So it arrived correctly. And finally, I will release my Coke can into the trash can. So I don't know if you saw it, but it went, oh, you can see it. It went inside. Interaction. So that's basically my mission. So next, I'll discuss about transferring into the real robot. So first, I'll discuss about the electrical system. The main computer used is a Godson TX2. The actuation system consists of two parts. The first one is the actuation of the wheeled platform, and the second one is the actuation of the robot arm. They are dedicated with independent microcontroller. I use the Arduino Mega, and those are Arduino board. So the Arduino board controlling the arm is connected to 8 motor drivers. Each motor drivers can control two motors. So we have 3 here. Basically, this increases the load current from the Arduino to the robotic arm. The other Arduino handles the controls for the full motor via dual channel motor drivers. So it's those 2. These motor drivers use their own integrated commands for Arduino to control the velocity of each connected motor. The system is composed of 4 sensors. The RP LiDAR A1, which is used for odometry, mapping, and autonomous navigation. Then we have the Intel RealSense D435 camera used for object detection. I also have a temperature sensor for health monitoring the electronic compartment. And finally, I have a battery life sensor to monitor the battery level. So the communication between ROS and the motors is handled using ROS serial. It basically handles the communication between Arduino and the ROS topics. here, the common velocity topic is used to send speed values to the motors. The first challenge that I've encountered here was in turning. Basically, I had difficulties in turning. It was especially for once it was resting, it needed like a linear velocity to turn. The main causes for this was the type of wheels that we use. I don't know if you see. So those wheels are beach wheels. They are made for outdoor environments, not really for indoor. So the contact with this wheel and the floor is not very, it's going to cause a lot of friction. So that blocks from turning. Another interesting thing about my system is that I use a four-wheel drive, and when the distance from the front to back is bigger than the left to right, it's gonna also have a hard time in turning. It will allow a bigger torque. So all of these components make it hard to turn. So solution here was first to change the surface material. Another temporary solution was to replace the back wheels with caster wheels. But yes, basically, I think that the best solution will be to change the wheels for indoor environments. Another challenge that I found was that the robot was slowly drifting on the right when setting a forward velocity. This may be due to the axle that was bent, the axle shaft connecting the front motors, that it was bent. That might be due to mechanical issues, design, because the robot weighs like 50 kilograms, which is a lot. So yeah, and solution for this for the future will be to redesign and replace the axle shaft, and also to implement PID controllers to correct for this drifting. I was able to still do the autonomous navigation parts. So I have a video demo of my simulation, of my demo. So it's using autonomous navigation, and it detects the dynamic obstacle, which is not part of the map. I put a new surface to allow a better slippage. Yes, because the controller that I use is skid steer, so it's supposed to drift. So it's supposed to skid. That's why I put this thin cardboard to allow a better slippage. For the autonomous navigation, basically I need to communicate with the LiDAR and the odometry topic. To access the LiDAR, I've used the RP LiDAR ROS package, and for the odometry topic, I worked with a laser scan mature odometry package. It basically uses the laser to get the odometry data. You can see it on the left side here. So yeah, my final challenge was related to hardware. I had a lot of issues actually. So the first one we talked earlier was the axle shaft that broke. Then I had the wheel hub making the connection to the wheels that broke too. And this resulted in a delay in working with the real robots. To solve this, like I said earlier, will be to redesign and replace with a thicker axle shaft. A temporary solution was to remove the suspension. So you can see that there is no suspension here. It was originally like, oh, I don't have a picture. I have a picture. Here we have the suspensions. If I zoom, oh, no. I can zoom, but there's the suspensions that I removed. And for the wheel hub, I had to 3D print a new one. So this wheel hub is made of plastic. So for the future, we'll have to use maybe metal for this wheel hub. Concerning the future goals, I have two types of them related to two different missions. So the first mission is the one we discussed about for the indoor environment. My goal was first to fix the hardware issues by redesigning the broken shaft, change the wheels to get appropriate wheels for indoor environments, implement PID controllers. I'm also interested in implementing IMU into laser scan matcher odometry package for a better odometry. And of course, get my complete demonstration of the fetch and carry mission, which includes the manipulation perception pipeline. My second type of goal was related to an outdoor environment. So the goal here is to compete for the University Rover Challenge, which takes place in, I think, California. But basically, it's an indoor environment. For this, it's a completely different problem. So I would like to use GPS combined with IMU for outdoor navigation. And I would like to implement extended Kalman filter for noise reduction from the odometry. And finally, I would like to implement new arm planners for faster planning trajectory computation. So yes, thank you for listening. I hope that you find my project interesting and that it inspired some listeners to continue working on this topic. Please let me know if you have any questions.
Thanks a lot, Jason.
Thank you.
Thank you. Very nice project and very nice presentation. So now it comes the moment of truth.
The moment of truth.
Yeah. So let's. We have here some questions for you. So we can start maybe. There were some people who was wondering if you could elaborate a little bit more on this planner thing. So why the DWA was not working, and what is the differences with the TEB?
So as I was saying, the main cause was to handle complex, especially narrow areas. But the main point was to the backward motion. Like for example, when I was setting goals inside this area, like a narrow area, it was getting there inside this area, but it's not able to come back. You know, once it's inside this narrow area, and I send a new goalpost outside of it, it will have a hard time to plan. It will get stuck basically. So that was the main cause to use this. Also, yeah, like I said, it allows more car-like maneuvers, so it's able to drive back and get overall better planner results. Yeah, it's overall was better for I'll say the local planner.
Okay, so we have somebody, some of the teachers that want to ask always about, they are very interested to see the notes that you are running. So I'm sorry, but to all the speakers, we have been asking the same question. If you can show the RQT graph with the notes of when your system is running.
Actually,
I think that you didn't close it. Yeah.
No, I didn't close it.
Yeah. RQT again. Yeah.
So I've closed the perception pipeline. Maybe you want me to launch it again? Because I have to go
yes,
back.
because then we'll have a complete.
Yeah, maybe I'll.
You can close our bases.
Maybe I'll start the simulation.
No necessary.
No.
Why?
I just want to go back to the. So I'm gonna use the navigation.
Sending back to the point of interest that detects the table.
Yeah.
It was, yes.
Sorry. Yeah, so I'm gonna use this window.
Just a command. I think that you have it on your notebook.
Cool. Let's go to point. So I'm gonna go back to the grasp position.
Oh, you remember.
So meanwhile, I think there was another question, which was, how does this service work? Can you explain how does this go-to-point service work?
Yes, so basically it's using so let me show you. I'm using a parameter file. Let me find it. It'll be easier to understand. So
Scripts.
Over. So I've set a YAML with my goalpost, with my grasp position and my release position, and it's gonna read this data. So it's a pose message. Let me check. So it's using so like I said, a string which I input my either the grasp position or the real position, and it has a pose message with the position and orientation. So basically, yes.
And those positions you extracted from where?
So those positions are extracted from the IMCL pose. So I did some testing from the IMCL. I've used the Téllez to manipulate my robot to go through the object to go to my goal pose. So basically the first one next to the table. So I had to find the correct distance, because if it's too far from the table, the arm won't be able to reach the graspable object. And my arm isn't that long. I think the maximum reach with my orientation pose was like 70, around 70 centimeters from the table, from the graspable object.
But then how do you manage? Because in order to grasp the object, so your robot has to be at a quite good position with respect to the can.
Yeah, so
and then how do you manage? Because the navigation has some tolerances.
Exactly, that's the part where I had to tune the planner, the TAB planner. I have it here. I set it some small goal tolerances from the orientation and the position. I've also set some low velocities. I have it here.
Why the low velocities?
For the turning part, when it handles narrow areas, it was more efficient to follow the path I set it low velocity for this to follow more appropriately the local planner. So the TB local planner. So yes, I've set it some pretty slow. Like the max is like 0.5 velocity. I've set it also the backward velocity, and the tolerances I set very low tolerances, like 5 centimeters.
But doesn't happen then that maybe because 5 centimeters is very low tolerance, then doesn't happen that sometimes doesn't reach the point and then it's kind of trying all the time, because the orientation is not 5 centimeters, but then it moves.
So it takes some time. It takes some time, but to correct the goalpost. But it arrives here. I've noticed sometimes it doesn't arrive completely. I'm not sure why, but it doesn't get through those 5 centimeters.
Yeah, because it's very low.
But it still arrives there.
Yes. So yeah, it's awesome. And also you show us. I mean, you show us live. You show us live, and it was impressive. But then with those so small tolerances, sometimes it may happen that you will not reach the goal. So you are lucky when it reaches.
So honestly, it's like maybe one time out of 5 it won't work. So I've encountered this.
Okay,
that was one of my challenge, but mainly it does the job.
Okay. Yeah. Also the
but
fact
I'm wondering why this. Because I've set this goal tolerances to 5 centimeters, and it goes there. It says that it arrives, but it's still out of those 5 centimeters.
Oh,
I was wondering why this happens sometimes.
Maybe it's because of the frame that is actually considering. Maybe you are considering one frame and the planner is considering another one. I don't know. Suggestion. But also the fact that you put very slow velocities in order to correct.
So that's why also, I've studied this to correct it. Maybe for me, I should decrease again. Its velocity.
Yes, maybe.
Yes.
Okay. And then, I wanted to ask you, why did you have to create a plugin for grasping?
So sometimes while I was doing some testing, so it's a known from Gazebo, it doesn't handle the physics properly, I will say. And sometimes it was grasping my objects, and while retrieving, it wasn't attached to the gripper. So I used this plugin to facilitate the attachment. So I use to facilitate the gazebo physics so that it attached to it.
Okay, so it's not actually grasping by friction but by let's say by a trick that we do.
Exactly.
Okay.
It's a trick, exactly.
Okay.
Yes.
Okay. Great.
Yes, the fingers, or for me, maybe too small. I don't know if maybe I have set it. It went back. It's here. So it was low. It's quite.
What happened there?
Not sure. If I go. So I can't zoom on here. It doesn't work. But my fingers, you see that they were quite small. So maybe I need bigger fingers to allow a better grasping.
But no, in gazebo it won't work. So that trick that you did is a common trick.
Or maybe like another graspable object, more rectangular, instead of a Coke can. Not see if you
like a prism.
Yeah, it will allow a better grasping, maybe.
But it's what you mentioned, that gazebo, the frictions are not properly handled.
Yeah, physics.
The physics, yes, of the friction.
Physics.
Okay, so then can we move to the RQT graph and see the
Oh,
graphs,
sorry,
even without the perception?
Sorry.
Oh, it's okay, it's okay.
We got lost.
We are here chatting.
RQT. Right.
Can you explain us a little bit about the nodes? What
So-
each one is in charge of?
So yes. So the move base is the main node for navigation. So it subscribes to the AMCL, to the localization, also to the map server to get the data from the map that we've created. What else does it take? It also takes the transformations from the robot state permission. And as I said, the my service server go-to point of interest. It also receives the data from the odometry, of course. And what else? It's the main. Oh no, also for the gripper. So
Do
yes,
you
the
have
movement
movie
is responsible for the gripper. Sorry, for the arm control.
Yeah.
Which is basically the composed, like I said, of the two controllers, the joint trajectory controller, and for the arm joints. So it's this one, the scaled pose joint trajectory, I called it, and the gripper action controller.
Okay. Then are you managing the gripper from within MoveIt? I mean, when you are planning?
Yes.
So it is included inside the group?
Yes,
Gripper.
exactly.
Okay.
Exactly. So the trick, I also did a trick here for the gripper. So the gripper action commander controls, it's a controller for executing like gripper command action for a 1 degree of freedom gripper. I've used a mimic plugin. Basically, I'm controlling one finger with my gripper action command, gripper action controller, sorry, and I use a mimic plugin to mimic my second finger, so that it's symmetric when it open and close.
Okay.
So, I have one question. So all these so we have seen more or less that this can be and has been more or less ported all the navigation part, but for the especially for the arm, for all the manipulation part. So you said that you are using some tricks like this mimic joint,
Yes,
tricks
there's
for the
two.
grasping. So what would be required to do in order to port to be able to use your
robot?
MoveIt package and everything in the real arm?
Yeah, in the real. So that's a good question. I haven't been thinking about this yet, but for me, so there is one thing too. I may have to.
I think we lost Jason.
Can you hear me?
Yes,
No,
now.
I'm sorry. I'm thinking.
Okay. So, but you were so
still.
so still that I thought that was frozen the image.
So can you repeat your question, Alberto? It's
Yeah.
basically how to transfer to the real robot the manipulation parts, right?
Yeah. So what work would more or less in general terms? What would be what is missing to do so that you can try and test your code in the real arm?
So first I have to allow the communications with the motor the motors of the arm. First, so yeah, let's say we want to control the arm joints. So it's composed of 5 motors. So I have to set a communication between the motors and ROS. A little bit like I did with the common velocity, which was allowing the communication between the motor wheels and ROS. So I've used ROS serial. I think I can use ROS serial to communicate between my arm motors and ROS topics. So I need to allow this communication first. The same for the gripper.
What are, and your robot arm is controlled by microcontrollers?
Yes.
And have you considered using micro ROS for them? Micro ROS is ROS2 for microcontrollers. It's for ROS2.
So I'm using ROS1.
Yeah. So
Okay, but that's a good point. I'll write it down.
It's a suggestion. Yeah.
So you said micro ROS?
Yes, micro ROS is ROS, and it runs on board, because now you mentioned about ROS serial. Then that means that you will have to communicate serially with the board, control board, Arduino boards. Exactly.
You have ROS serial Arduino, yes.
Yeah.
So basically, I have like an Arduino code. So yeah, I have Arduino codes, the controls code.
Okay.
And so if I understood this, micro ROS is to communicate
to have
like
ROS2 in the Arduino boards.
Okay.
So, and then it's publishing directly in ROS2 directly, so you don't need anything, because the boards, they are already publishing and receiving orders in ROS topics.
Okay, I wrote it down.
Yes.
Thank you.
Sure. One question here about the ARM also. So when you are using planning, so how do you prevent that the ARM collides with the mobile base?
So actually, I didn't think about it. It doesn't really. I use what solver that I use. You saying? I think the solver handles it.
Well, no, it actually can find solutions that go.
I didn't have this problem. I didn't think about it honestly.
Yeah, okay.
I thought that the solver was handling this, so you're thinking I should use a kind of sensor?
No, it's on Move It. In the configuration of Move It, you can define to what it is attached. And then
actually, I think it is.
It is already done, probably, because otherwise it would have collide. Yes. Okay. So then it's defining this as a collision thing that can handle. So it's not planning that part, but it's taking into account for collisions.
Yeah, so you are passing the URDF of the full robot to move it,
okay.
right? It's not only the URDF of the arm, but it also contains the rest of the robot, right?
Yes, exactly.
Yeah, then that's why it's automatically handled already, because it already knows about
Move It knows. Move It knows. Okay, but doesn't for the table.
Yeah, exactly.
So for the table, it could happen that it can crash. Actually, did it happen?
No.
Yeah. Again, lucky. Twice.
No, I was setting the offset for the table in the height. I set an offset for the height for the Z position.
Okay, and then about running this on the real robot. So
I was able only to do the navigation part because of the coordination.
Do you have to change something, or you just put the code there? Run it.
No.
I mean,
first I had to do the. So you're meaning about my ROS codes?
In the computer, I don't know if you are running that on the computer of the robot or a
Yes,
remote.
exactly.
Yeah.
Yes. So first I have two things. I have like I said, the controls code, and also the simulation files. So I had to remove a few things. Also, I have to change a few things.
Why?
Why? I have to remember, because so first, obviously, I had to remove the simulation, the gazebo simulation, because I don't need it anymore.
Oh yeah. But
First, that's the most important thing.
No, but I mean,
Since,
in terms of modification of some parameters, maybe.
Yeah, the ROS code.
Yes, exactly. So, yes, I need to change some parameters for the planner, for the TEB planner. So I had a few issues with my robot. Like I said, it was in turning. It's not able. So there is a lot of friction. My robot, I was having a hard time turning because, like I said, of the wheels, and they're not made for indoor. So it was having a hard time turning. So I increased my velocities in the planner, angular velocity, especially. This was one thing. I've also, that's the only thing really that I've changed for the navigation. Oh yes, for the odometry, I needed to get my odometry topic. So I don't have the same odometry topic. I've got my odometry from a laser scan matcher. Basically, I'm getting the odometry from the LiDAR.
Oh, okay. So you are not computing the odometry with encoders on the wheels.
So no, we wanted to do this, but the wheel encoders are not very useful here because I'm using the skid steer drive. And it's like 4 motors, so it will allow the robot to slip, and this will not be useful for the wheel encoders if it's slipping.
But for the wheels?
Yes.
But for the wheels that are rotating?
Yes.
That you can compute the odometry.
So it's not useful to use wheel encoders when there's slippage.
Well, based on
because there is going to be some slippage. It's going to rotate,
Yes.
But it's the encoders won't be useful here because of the slipping.
Well, on the front ones, yes.
So yeah, basically I want to use the LiDAR.
Okay. And then also you mentioned that you wanted to use the GPS and.
So yes, this is for a different problem.
Yeah,
for
outdoors. Yes. I wanted to recommend you the robot localization package. Do you know that one?
Robot localization package.
The robot localization package, because you mentioned that you wanted to, in the future, to create an extended Kalman filter and integrate those. It's already done there. And you can introduce the sources, GPS, odometry computed by laser. Also, you can introduce, and then it's going to mix all those sensors and produce you a very good localization.
So I've seen one, but I think it was a different name. It was EKF package, I think. And basically, you need. So there was, if I remember correctly, there was 3 sources of because it's basically sensor fusion.
Sensor fusion.
You two are talking about the same. Yeah, actually.
I would say.
Yeah.
Oh, it's the same. Okay.
Yeah.
So yeah, I remember it basically uses the odometry message and 3D also, 3D odometry, 3D visual odometry from either a camera, but I was more interested in using the GPS. Because the mission is like outdoor and it will be long distance. So I think it's better for me to combine the GPS with the IMU and use EKF extended Kalman filter to reduce the noise reduction.
Okay. Let me ask you one question about the hardware problems that you have. So what would be your recommendation to to avoid those inevitable or reduce those inevitable hardware problems like the hub breaking?
Sorry, I didn't understand the question. Sorry.
So what would be your recommendations to
Yes.
alleviate those hardware problems?
So for me, so it depends. There's two things. First, for the indoor environment, for me, we should change the wheels. They're not appropriate for indoor environments. So,
but
I want to use the mechanism wheels.
Yeah, but I mean, not in this specific case, but in general. So for your next project or for your next testing with this robot, so how would you, because hardware is very expensive.
Yes.
And also takes a lot of time. So how would you proceed differently from now so you can reduce even more your hardware problems?
So, like I said, I mean, do you want me to, for me, so you're saying finding a solution with the same hardware?
Yes. So,
okay.
Yeah, okay.
For me, also, like I said, so redesign.
Okay,
me,
let me rephrase.
Like some mechanical issues that need to be changed because it broke. So why will I choose the same hardware if it broke? If I did like, I don't know, I didn't do that much testing because it was broke. So with this such less amount that I spent on testing, it broke. So for me, I should find hardware, more mechanical hardware. We should need to change the design of the hardware. Like, you know, like it was, for example, when the wheel hub, when I was giving an angular velocity, it's slipping a lot. It's blocking the wheels from rotating. And the wheel hub, the inside of the wheel is made of 3D prints, plastic.
And
this 3D prints, I didn't put a picture, I wanted to, but it broke.
Yeah.
And so I was lucky, we had a 3D printer at my university. So we were able to correct it. But we need to change this maybe 3D part with metal.
Okay.
And also the shaft, we need to design a thicker shaft.
Okay.
Or like I said, for me, it may work in a different environment, maybe in the dirt. So like I said, for the outdoor environment, I would like to keep with this robot, but it will be able to slip maybe in the dirt, in the grass, the grass. So it depends on which environment I want to go. For outdoor, I'll stay with this. I think it will have overall better results.
Okay.
So, you know, it will allow a better turning. Reduce the friction.
Yes.
So summarizing, maybe it would be to spend a little bit more of time in designing the robot,
exactly,
and having clear where it's going to be used, because it's not the same to design a robot for being used indoor with rigid floors and so on, or for being in Mars, which the surface is completely different, or for being in a beach. So have very clear the purpose of your robot, where are you going to be use it, and then based on that, design it accordingly, right?
Exactly. We have to put the brains into the design. At the end, for me it was a good experience that it broke, because I learned a lot about the mechanical design, and I'm able to explain you guys all of this because it broke. So I'm happy it did broke. But in a way, I'm not very happy, but I learned a lot. I mean.
Okay, so thanks, Jason. We are going to leave it here.
Okay.
Thank you.
Thanks a lot for your presentation.
Thank you very much. Thank you.
And so this is all for this ceremony. It's we've had some ups and downs. We started with some live problems. Hopefully, now we have been able to solve them, and we have finished it better. So yeah, thanks for being here with us. I hope that you have enjoyed all the presentations and that you have learned something with them.
Yeah, and if you want to check where we had those problems, just rewatch the video. It's going to be published online on this channel, on the same place, so you can rewatch and see and have a laugh while we have no clue what is happening there and trying to solve it.
Yeah, and we, just so that you know, we will have more project presentations from other master students at the end of January. So
well, yes, that's because what just finished now, it was the full-time part of the master class to become a robotics development. So I didn't explain that before.
Yeah. So we had the full-time students who are the ones that have been presenting today. They are finishing already the master class.
The master class finished.
So they are about to graduate, but we still have another batch of students who are the part-time students who are going at a slower pace. So they are going to finish more or less by the end of January. And then by that time, they are going to do their project presentations, which are going to be completely different, and I'm sure that are going to be super interesting as well.
And in case that you like it, what those guys, they have been presenting, they learn how to do all those things by taking the master class that we produce at the Construct. And in case that you would like to follow the same path, remember that we have another batch by January 2023, and you can find a link with more information here below the video.
Yeah, so become the next ROS2 developer, master. So yeah, let's.
Oh, actually, let me tell you that I met yesterday one of our students who already is working for robotic company. So by taking our master class, and then he's already working for robotics company who is based. This company is based on ROS. So.
Yeah, and so it's very interesting because he's a student from. I think it's from Singapore. It was.
No, he's
Taiwan.
from the States.
From the States. Yeah, but he was living in
Thailand, in Taiwan.
In Taiwan, yeah, and now he's moved to Spain to work at a robotics company. So it's an amazing story. Yeah.
Yes, interesting. Maybe we'll feature the story. Okay, let's finish here because it's very late already, and see you.
Yeah, bye, and don't forget to keep pushing your
ROS learning.
Bye.